Chapter 1b, the kinetic model. In this section, we're going to introduce the kinetic model, and we'll see what is ideal gas at the microscopic level and how this leads to the ideal gas law. And we're going to show some important applications from kinetic model. In kinetic model, the gas molecules are considered molecules of mass in ceaselessly random motion, obeys the law of classical mechanics. The size of molecules is negligible, and their diameters are much smaller than the average distance traveling between collisions. In other words, the gas molecules are considered dots moving randomly in all directions and collide this wall, and they collide with each other, but they obey the law of classical mechanics. The molecules interact only through breath and elastic collision. That means the energy, whenever they collide, the energy is conserved. So if we know the velocity of the traveling of the gas molecules, we can calculate the force exerted on the wall, and therefore we can calculate the pressure. Before we do any of the calculations, we must know the velocity of the gas molecules. It turns out that if we have a collection of molecules, then we expect molecules may have different velocity. Some go faster, some go slower, and this is a distribution of velocity. So here is the drawing showing you the velocity distribution. So for example, some molecules has a velocity, let's say this is 20 meters per second, and the percentage of the molecules has this velocity is 10%. But some actually have very high velocity, let's say this is 80 meters per second, and the percentage of the molecule has this velocity is 5%. Okay, now here is the highest percent of molecules, and the velocity here is 40, let's say 40 meters per second. So 40 meters per second is the has the maximum probability or percentage of molecules. So you have a distribution of molecules. Some go faster, some go slower, and you need to know the percent of molecule has a certain velocity, and this is called the velocity distribution. Now the velocity distribution function also describes the probability. For example, the probability of a molecule has a velocity v and v plus a very tiny change dv should be the percent of molecule has v times the range dv. Okay, so from v1 to v2, what is the probability of a molecule has the percent of velocity from v1 to v2 should be integration of this velocity distribution dv integration from initial velocity v1 to v2. Okay, so the most important thing we need to know is this velocity distribution. Okay, if we know this one, then we can calculate the probability, we can calculate the speed, the force, momentum, and the pressure. The velocity distribution function is derived based on an equation called the Boltzmann distribution. Boltzmann distribution is one of the most important equation from statistics. It tells you what is the percent of molecule has a certain energy, which is a constant times e to the negative the energy that you are interested divided by kt. K is called the Boltzmann constant, and therefore the percent of molecule has a certain energy is a function of temperature. All right, when you change temperature, then more molecules has higher energy. All right, so it's a function of temperature. Now, if we want to find the velocity distribution, we know the energy is related to velocity by half mv squared. So we just plug in here, okay, energy, all right. So, and also take care of the all directions, because the molecules go to all directions, and in geometry we know the area of this spherical is 4 pi times r squared. The r in this case is the velocity, so 4 pi times v squared. That's the surface area. So that takes care of all directions. And for one direction is this equation. So plugging these two equations, we should get this equation, which is called the Maxwell-Boltzmann distribution. This equation is about the speed. Okay, so the speed is 4 pi v squared times the mass of the molecule divided by 2 pi k Boltzmann constant, temperature 3/2 power times exponential to the negative m is the mass, v is the velocity or speed squared divided by 2 kt. So this is an important equation because all the calculations later are based on this equation. So we can calculate the percent of molecule has a certain velocity. For example, what is the percent of molecule has a velocity 50 meter per second? So you just plug in here, speed 50, all right, and then temperature is given, mass, temperature, Boltzmann constant. Then you can calculate the percent. What is the percent or fraction of molecules has a velocity 50 meter per second? Okay, based on this equation. So if you plot it, you should get the familiar curve like this one. Some go fast, the percent, small percent of molecule has a low speed, small percent of molecule has a high speed, majority of molecule has a certain speed here called the most probable speed. Let's plot this equation, Maxwell-Boltzmann distribution function for argon gas. So first, plot at 298 Kelvin, and you can see the most probable speed for argon at 298 is about 400 meter per second. Of course, some argon gas move slower, let's say here, some have 100, 200, 300, but mostly 400, and some higher speed, all right, but the percentage are small. Some even have 800, but the percentage here may be only 0.00000, very, very small percent, but mostly 400. That's the most probable speed at 298 Kelvin. Now, if we plot the same gas, but temperature change to 1000 Kelvin, then the most probable speed now increase to about 700, okay, 700 meter per second is here. Instead of 400, it moved to 700. So increasing temperature increase the maximum speed, okay, the max percent of molecules of the speed. So the most probable speed increase. Some molecule you can see goes to very high, 1000, even have 1500 meter per second. But the majority, the most probable speed is 700. Okay, now let's apply this equation to different gases. So this is argon gas, but this is the one for krypton, and this is for neon, neon gas, using this equation at the same temperature. And you can see the most probable speed for krypton is about 300, argon 400, neon about 500. So you see, even though you have a distribution, all right, even for the smaller molecule, neon, it can go fast or slow, but the most probable speed for neon is higher than argon, which is higher than krypton. So the smaller molecule in general move faster, and the heavier molecule moves slower. We just derived the Boltzmann-Maxwell distribution function, so we know what percent of molecules has a certain velocity. So how do we calculate the average speed? Okay, average velocity. To do that, first we need to have an equation to calculate average value in statistics. So if you already learned the statistics class, you know the equation. All right, let's look at an example. Suppose we have a class of many students. 5 of the students have a grade, let's say -6. 15 students -2. 50 students got 0. 10 students got 1. 5 got 3. 10, 4, 5 students got 5. So these are the grades. These are number of students that have a certain grades. So what is the average grades in this class? Okay, to calculate the average grade, you need to calculate the total grades. So because 5 students have -6, so the total grade is 5 times -6. And 15 has -2, so 15 times -2, and 50 has 0, so times 0, 10 times 1, all right, 5 times 3, you keep going. So you add all together, and so you use x1, which is -6, times n1, which is 5, plus x2, which is -2, times 15. And then you add all these grades with the number of students, add together. So this is the total grades divided by the total number of students, and that gives you the average grade for this class. Now in mathematics, this equation you can separate into many individual equations. So this can be x1, n1 divided by the total number of students, and then x2, n2 divided by the total number of students, and then x3, n3 divided by total number of students. So you add all individual grade number of students times grades divided by total number of students. Now if we look at this equation, so n1 divided by n1 plus n2 plus n3, and that is actually the fraction of the number of students that has x1. And this one, n2 divided by n1, n2, n3, that's the fraction of number of students that has x2, grades x2. So this equation becomes this. The grades x1 times the fraction of number of students has x1. x2 of the grades, which is -2 in this case, times the fraction of number of students that has these grades. Okay, so fraction of number of students in statistics, if we have many students, fraction of number of students of x1 is also the probability. So P means the probability of the student has x1. Okay, x1 times p x1, x2 times p x2. So in this table, we can add 2 columns. All right, so the column here is to calculate the fraction of number of students that has the certain grades. For example, 5 divided by total number of students, 100, give you 0.05, and then 15 divided by 100 give you 100 divided give you 0.15. So you calculate the fraction and then use this column times the grades added together. All right, so that give you the grades, average grades. Okay, so this is an important equation in statistics. If you want to calculate the average value, you use individual value times the percent of the either students or the molecules that has this value, all right, or percent or probability. Okay, so that's the equation to calculate the average value. So if you calculate average speed, you use each speed times the percent of molecule has this speed. And you can also calculate the average speed squared. Okay, so here x squared, all right, average, you can use individual x squared times the percent of molecule has this, the percent have this value. So in statistics, you calculate any average value by using the individual value times percent of the items that has this value. Okay, so that's a very important equation. So with this equation now, let's calculate the average speed with the Boltzmann-Maxwell distribution. Now, if we have a collection of nitrogen molecules at 25 Celsius, what is the average speed, or the mean speed, means the average speed. So to calculate the average or mean speed, we use the equation we just derived, and that is the individual speed times the fraction of molecules have this individual speed. You add all the possible individual speed times the fraction. All right, you add all together. Okay, so one way to simplify is use this symbol. All right, it's the summation of individual speed times the fraction, or the probability have this speed added together. Now, if the speed distribution is a continuous function in calculus, and this becomes integration. So integration, individual speed times the fraction, or the probability of the molecule has this individual speed. Add all together from the lowest speed to the highest speed. So that's integration. Okay. Now this the fraction of molecules has a certain speed obeys the Maxwell-Boltzmann distribution. So here is the Maxwell-Boltzmann distribution. And notice that here are all constant. So when you integrate, you can move all these constant out of the integral. So these are all the constant, and inside you have speed v times v squared, that give you v to the third power, and e to the negative mv squared divided by 2kt integration. So how do you integrate this? One way to do it is look at a calculus textbook. You will find the standard integral. This integral says that the integration of any variable x to the third power times e to the negative a times x squared, integration from 0 to infinity, it gives you 1 over 2a squared. So if you compare these two equations, you will see that we can replace x by v. Okay, so exchange x, v. Here is x squared, here is v squared. So the variable, instead of x, you use v. But what is a here? So in this equation, a is the one in front of v squared. So that is m divided by 2kt. Okay, so m divided by 2kt. That's a. All right. According to this equation, integral should be 1 over 2a squared. So here should be 1 over 2a squared is m divided by 2kt squared. Okay, and that will give you, so note that 2 squared is 4, and 2 divided by 4, okay, so give you 2. So 2k squared t squared divided by m squared. Okay, so that's the integration for this one. And then you multiply this coefficient 4 pi m 2 pi kt to the 3 over 2 power. When you do that, all right, I suggest you to try it, multiply by this integral. The answer is this equation, all right, square root 8kt divided by m pi. Okay, that's the mean speed or average speed. Now mean speed, we can use a symbol, this symbol c bar. That's the average or mean speed. Okay, it's also this one, which is square root 8kt divided by m pi. Now in this equation, K is the Boltzmann constant. Okay, it's a constant. You will see this later. Now the m is the mass of one nitrogen molecule. Okay, one molecule, the mass and the pi. So sometimes it's inconvenient to use one molecule mass to calculate this equation. So instead we can use molar mass. So how do you do that? Well, if you you have 8 kT divided by m pi. Now if we inside the square root, if you times Avogadro's number on the bottom and also on the top, then that doesn't change the value. So you can do that. But m mass of one molecule times Avogadro's number, that's the molar mass. So you get molar mass times pi. Note the difference. This is small m, that's the mass of one molecule. Here is the molar mass of nitrogen. All right, you can find it easily from periodic table. And then here 8. Now K is a Boltzmann constant. When Boltzmann constant times Avogadro's number, it turns out that this is just the gas constant. So you have 8R gas constant times T. And therefore these two equations are equivalent. Either you can use 8 kT over m pi square root, or you can use square root 8 RT divided by pi m. So it's very common later you will see, whenever you see an equation includes a k and m, you can always replace by r over m. So this is the mass of one molecule, this is molar mass, this is Boltzmann constant, this is a gas constant. So either equation can be used to calculate the mean speed. Now because molar mass is easier to use, so usually we can use the second equation. So your nitrogen is about 28, so use 28 gram. Now gram you need to change to kilogram because that's the SI unit. So kilogram, so you need to times 10 to the minus 3. 28 gram times 10 to the minus 3 becomes kilogram per mole. And then pi R is 8.314, T is 298 Kelvin. So plugging everything, so again please try it, and the answer you will get is 475 meter per second. Okay, so that's the average speed of a collection of molecules at 25 degrees. Some molecules go faster than 475, some go slow, but the average, okay, by statistics is 475 meter per second. And so that's how we calculate the mean speed. In the last slide, we showed how to calculate the mean speed or the average speed of nitrogen. Now you can use the same equation to calculate the average speed for argon or helium for any gas. It's square root 8 kT divided by pi m. Now sometimes we want to calculate the average value of V squared. Instead of average V, we want to calculate the average V squared. Now when do we do that? Okay, why do we need V squared average? So suppose we want to find out the average kinetic energy. So kinetic energy, which is calculated by the kinetic energy of molecule 1 plus kinetic energy of 2, you add the kinetic energy of all molecules divided by the total number of molecules. That's the average kinetic energy. And the kinetic energy is calculated by half mv squared. So you have different speed for individual molecules. So you have half mv squared plus half mv2 squared plus half mv3 squared. So you add all the kinetic energy of individual molecule divided by the total number of molecules. And this equation you see here, v squared, they all have half m, half m, half m. So you factor out half m times n v1 squared, v2 squared, v3 squared. You add all this v squared divided by n. So what is this one? V squared divided by n, that is the average v squared. And therefore, you see, whenever you want to calculate average kinetic energy, you are not using the average speed to calculate. You are using the average v squared times half m. So half m times average v squared. Note the difference. Instead of the v squared, this is you average first and then square it. Here you actually average the v squared, all right, times half m. That gives you kinetic energy. So how do you calculate the v squared average? Okay, in the last few slides, we showed anything when you calculate the average value. Okay, so for in this case is v squared. How do you calculate average? You just use average. You use individual average speed squared times the fraction of molecules have this speed. Add together v2 squared times average v, the percentage of molecules has this speed. You add all together. So that's how you calculate. Okay, again, because v is a continuous function, and therefore you use v squared, all right, times the percent or the fraction of molecule has this v, which is Maxwell-Boltzmann distribution. Again, we move out all the constant out of the integral, and here inside, because now it's v squared, here is also v squared, so you get v to the 4th power times e to the negative mv squared divided by 2kt. To integrate this one, again, we look at a standard integer, which says any variable to the 4th power e to the negative ax squared, integration from 0 to infinity should give you 3/8 square root pi over a5, a to the 5th power. So again, x is replaced by v, and here x squared is v squared, and so the important thing is to find what is a. So in this equation, again, a is m over 2kt. Okay, and so plugging here, all right, a becomes n divided by 2kt, and you can calculate the integral. So after that, you multiply by this number, and again, I suggest you to try it, and the answer should be 3 times kt divided by m. Okay, so note that again we see k over m. If you times Avogadro's number on top and the bottom will becomes molar mass, the top becomes gas constant, and so you will get 3 kt over m or 3 RT over m, big M. So here is the big M, here's the small m. One is the mass of one molecule, one is the mass of the molar mass. All right, so that's the average value of v squared. The symbol is just okay. So here is 3/kt or 3 RT over big M. That's equivalent, okay, to calculate the average v squared. Now in statistics, we sometimes square root this one. After square root, we call this root mean square speed, because this is the mean square speed, okay, or the average square speed, and we root it, so square root it, and that's called the root mean square speed. Okay, so if you square it, and that will give you the average value of v squared. Okay, you have root mean square speed, and then you square it, you get the average value of v squared. Okay, so how do you calculate average kinetic energy? Okay, according to here, you should use half m times the average v squared. Not this, so average squared, v squared. So average v squared, or we can write as half m times c squared, because c is the square root of this one, and then integrate square it, so c squared. So now we are ready to calculate average kinetic energy of a certain gas phase. Okay, so for individual molecule, the kinetic energy is half mv squared. But if we have a collection of molecules, different molecules has different speed, and therefore you need to average it. So what we have from the last slide is half m times the mean square speed, okay, mean square speed. Okay, so the mean square speed, we just derived the equation, is 3 over kt, 3 kt over m, or 3 RT over m. All right, so plug in here. This is from last slide. So plug in here. So what you have is half m times m3 kt. Okay, so what we have is 3 over 2 kt. Okay, so the average kinetic energy is 3 over 2 times kt, and this is a very important equation. And what it says is that for all gases, no matter what the gas is, nitrogen, neon, helium, they all have the same kinetic energy if temperature is constant. Why? Because this equation does not have mass. And so it doesn't matter whether the gas is heavier or lighter. It has the same kinetic energy as long as it has the same temperature. So gas molecules possess the same kinetic energy at the same temperature. Temperature is a measure of average kinetic energy. Okay, increase temperature, increase average kinetic energy. Now pay attention to this. Kinetic energy same doesn't mean they move at the same speed. All right, because kinetic energy is half mv squared. If the kinetic energy is the same at a certain temperature, kinetic energy is the same. But if mass is heavier, then speed must be smaller. Okay, high mass, smaller speed, because the product give you the same kinetic energy. All right, the lighter, smaller the mass, the faster the molecules move. But when you multiply by this equation, you should get the same kinetic energy, average kinetic energy. The average kinetic energy is 3 over 2 kt. Okay, it's a very important equation to calculate average kinetic energy for all gases. With the Maxwell-Boltzmann distribution, we are now ready to derive ideal gas law from the kinetic model. So in kinetic model, molecules are just dots moving randomly in all directions, obeying classical mechanics, the Newton's law. And also the pressure is due to the collisions of the gas molecules or particles with the wall. Okay, so in this diagram, the gas molecules moving in all directions, and they constantly strike the wall. So that will give you the pressure. Now in physics, pressure is calculated by force divided by area. And so in order to calculate pressure, we need to know the force. According to Newton's law, the force is mass times acceleration. And acceleration is the speed change over time, or the derivative of speed over time. And therefore, force can be written as m times dv over dt. Okay, for mass times acceleration. Now the mass times dv, that just equals the momentum change. And so dp. Okay, so dv means v2 minus v1. You times m, so m times v2 is p2. M times v1 is p1. P is the momentum. So the momentum change over time. Okay, that's the force. And therefore, in order to calculate the pressure, we need to calculate the momentum change over time. We need to calculate the momentum change in a interval d delta t. Notice there are a large number of molecules, so we need to look at the average. So we'll see in the next slide. Let's first calculate the momentum change for one molecule collision with the wall, and then we add the momentum change by other molecules that collide with the wall to calculate the total momentum change. So suppose there's one molecule moving in one direction like this, and it has two components. One is along x direction, one is along y direction. So this is Vy. So the momentum before collision along x direction is mvx. Now, because the collision is elastic, so think about the ping pong ball. When it strikes, let's say this is a mirror, it go backwards with the same speed, but change direction, but the angle here is the same. All right. So what you have is you're moving towards this direction, and the y component is the same. It doesn't change the y component, but the x direction, the value is the same, but it's opposite direction. So negative. So negative momentum along x direction becomes negative mvx. So this is before collision along x direction. This is after collision along x direction. So what's the momentum change? Is the final minus initial. So here is the final after collision minus initial before collision, and we just want to calculate the value. So we use absolute value to see how much change, and that gives you 2 times mvx. Okay, that's how much momentum change after collision of one molecule along the wall. To calculate the total momentum change, we need to know how many molecules collide with the wall, and to do that we need to give a time interval. So let's say delta t, that's the how much time we look at the number of molecules collide with the wall. Okay, so what kind of molecule that has enough time to collide with wall? So if time is delta t, and if the molecule has a speed vx along x direction, then the distance that it can travel is vx times delta t. And so if the distance is from the wall to here, all right, that's vx delta t, then any molecule inside this distance will be able to collide with wall. Any molecule further away from this distance, okay, will only move to here, vx delta t, which cannot collide with wall. In other words, the distance away from the end of the wall is vx dt. So within this distance, that's the molecule that can collide with wall. So what's the volume of the molecules that can collide with wall? Is the distance times area A. Okay, so the vx delta t times area, so that's the area, that's the volume. Okay, any molecules inside this volume has the chance to collide with wall. Any molecules that outside this volume, all right, they don't have chance to collide with wall. So how many molecules? Okay, the molecule is the volume, which is vx delta t times area, that's the volume, times the density, number density, which is the number of molecules per cubic centimeter. And that's how, so the volume times volume density give you the number of molecules that have a chance to collide with wall in the time delta t. Okay, but in statistics, whenever you have a molecule moving towards the right side, there must be one moving towards the left side. They have equal chance, and therefore not all of them will collide with wall, only half of it. So you times half. Okay, so half Vx delta T times A times the number density is the total number of molecules that can collide with the wall on the right side at time interval. Okay, so next slide, we're going to calculate the total momentum change. In the previous slides, we first showed that for one molecule, when it collides with wall, the momentum change is 2mvx along x direction. So we also show that at the time interval delta t, the total number of molecules that can collide with wall is half vx, the velocity along x direction, times the time interval times area times the number density. And therefore, the total momentum change is just the product of 2mvx times the total number of molecules that collide with wall. So 2 will cancel each other, and Vx becomes squared. And you have number density, you have area, the time interval, the mass of one molecule. Okay, so this is the total momentum change in the time interval. But at this point, we need to think about the collection of molecules that has different velocity. It has a distribution, so they don't have the same Vx. Some are faster, some are slow. They obey the Maxwell Boltzmann distribution, and therefore you cannot use one Vx to calculate the total momentum change, and you have to use the average Vx squared. Okay, so the average Vx squared is the mean square speed along x direction. So here we write as the number density, area times time interval mass times the mean square speed along x direction. Now at this point we don't have this, but we have the mean square speed. Okay, now it's about 3 dimensions. So any speed, you have x direction, you have y direction, you have z direction. So it's vx, vy, vz. Now, because in statistics, all directions are random directions, they have equal opportunity. So along x direction, the average should be the 1/3 of the v square speed, the mean square speed. So along x direction is 1/3. All right. So this one we already know. Okay. So plug in here. So here is the total momentum change in the time interval delta t. How much momentum change? You need the mean square speed, which we already know. So we'll see in the next slides to calculate the momentum change and then calculate the pressure. Let's summarize how we calculate the pressure. Okay, in a kinetic model, molecules are just dots moving randomly in all directions, and they also constantly strike the wall, and that's the reason for the pressure. Okay, and so the pressure is calculated by the force divided by area. The force is due to the collision of the molecules with the wall, and we show that the force is momentum change over time. And last slides we show the total momentum change is the density, number density divided by 3 times area times the time interval times mass times mean square speed. So according to this equation, you divide by delta t, so delta t will cancel. You also divide by area, and so area cancel. So what we have is the number density divided by 3 times mass of one molecule times mean square speed. Okay, so what is the density? Number density is the total number of molecules divided by volume. Total number of molecules can be calculated by number of moles times Avogadro's number, and then divide by volume. All right, so plug in here. All right, what we have is 1/3v number of moles molar mass. Okay, why is molar mass? This is the mass of one molecule. This is Avogadro's number. When they multiply, you get molar mass. And then mean square speed. Okay, so what is mean square speed? Okay, if you go back to the few slides, you will see mean square speed is 3 kT over m, or 3 RT over m, molar mass. Okay, so if you use this one, replace this, so 3 cancel each other, and m, molar mass cancel each other, and what you have is RT over nRT. So so pressure equals nRT over V. Okay, and that's exactly the ideal gas law, or PV equals nRT. All right, so here we directly use mean square speed. Now if you use root mean square speed, then you need to square it. All right, you get this one. All right, so what's the conclusion? The conclusion is kinetic model, all right, is the model for ideal gas. So what is ideal gas? It's just the dots, okay, moving in all random directions. We constantly strike the wall, give the pressure using statistics. We can show the pressure obeys ideal gas law, PV equals nRT. We have mentioned several times the most probable speed. So if this is the Maxwell-Boltzmann distribution, the most probable speed is the speed that has the largest probability, or the percentage. All right. So how do you find out the most probable speed? Now in calculus, if you have a function, the maximum is calculated by setting the derivative to be 0. Okay, so we are going to skip all this. If you are interested, you can derivative of this Maxwell-Boltzmann distribution. Let this to be 0, and you can find out the speed. All right, is 1 over b negative square root 1 over b. B is this number, so plug in, so you get most probable speed is the square root 2 kT over m, or square root 2 RT over m. All right, so we showed several important speed, the most probable speed, the average speed, the mean square speed. We're going to summarize in the next slide. So here are the 3 special speeds. The most probable speed is the speed where the probability, or the percentage of molecule, has the maximum. Okay, the equation we just derived is 2 RT over m. Now the average speed, well, you can calculate by the all the individual speed. You add all together, divide by total number of molecules, and the equation to calculate is square root 8 RT over pi m. Okay, now the mean square speed, all right, is calculated by v1 square, v2 square. You add together, divide by total number of molecules. Now if you add a root, that's called the root mean square speed. The equation is square root 3 RT over m. Remember, this is useful when you calculate, let's say, kinetic energy. Okay, you have v squared. So if you have many molecules, you need a root mean square speed to calculate the average kinetic energy. Okay, now all these speed, they have root RT over m, RT over m, RT over m. So all speed increase as the square root of temperature and decrease as the square root of m. Now for the most probable speed is the square root 2 times RT over m. Here average speed is square root 8 divided by pi. Now 8 divided by pi, 8 divided by pi is about let's say 2.5 3 somewhere like that. And the root mean square speed is square root 3 times RTOM. So one is square root 2, one is square root 2.3, one is square root 3. So they are all very close, all right? Okay, and also the root mean square speed here is the highest, and then the average speed and the mean and the most probable speed. In the following few slides, we are going to look at some applications of kinetic model. First one is a collision frequency, Z. Now, collision frequency is defined as the number of collisions made by one molecule in a unit time. In other words, every second, how many collisions does one molecule make with adjacent molecules? Okay, to calculate collision frequency, let's assume molecules A move towards the right side, and actually we freeze other molecules, just let A move with a speed. This speed is called relative speed. Okay, now relative speed is commonly used in physics. For example, if two cars both move to the right direction with the same speed, let's say 40 meters per second, then to the first car, the second car it does not move at all because they are moving at the same speed. All right, so to A, the B has a relative speed 0. It doesn't move. Now, if A move from 40 miles per meter per second, but the second car move 50 meters per second, then they are approaching each other. So for a person in A looks at B, it's going towards B at a relative speed 10 meters per second. Okay, so that's the relative speed. All right. Now, if two molecules moving towards each other at a perpendicular direction, the relative speed can be calculated to be square root 2 times the average speed. Okay. So now let's calculate how many collisions if A move at a relative speed C. Okay, so relative speed. So how many collisions? Now look at one molecule B, which is just contact with A. Okay, so then each have a radius r, and so the distance between the center to center is just the diameter of the molecule. Okay, each molecule is the diameter. And if you have another molecule, let's say C is further away from B, then this will not collide with A. But if it's closer here, then it will collide with A. So B is the molecule that is the last molecule that can collide with A. In fact, the center of the B forms a cylinder. Here is the blue cylinder with radius d. Okay, that's the radius. All right, d. And the length of this cylinder is the speed or relative speed. Okay, so here let's see. So the relative speed times the time interval, that's how far it moves. Okay, speed times time, that's how far it moves. So that's the length of the cylinder times the cross-section area, and that gives you the volume of this blue cylinder, and then times the number density. That gives you how many molecules inside this cylinder that can collide with A. Okay, any molecules outside this cylinder will miss the collision. Okay, so that's the number of collisions made in the time interval delta t with molecule A. All right, so what's the collision frequency? You need to divide it by time. Okay, so when you divide it by delta t, you get cross-section area, relative speed times number density. So that's the collision frequency. Every second, how many collisions it make for A. Now here is the relative speed, and the relative speed can be replaced by square root of 2 times average speed. So the final equation to calculate the collision frequency is cross-section area times square root 2 times average speed times number density. So let's calculate the number density. So number density is calculated by the total number of molecules divided by the volume. And the total number of molecules is the moles times Avogadro's number divided by volume. And N divided by V can be calculated using ideal gas law. So PV equals nRT. So N over V is P divided by RT. So plug in here, we have then number density equals pressure, Avogadro's number divided by RT. So R constant can also be written as Avogadro's number times Boltzmann constant. So here goes here, and the Avogadro's number can be cancelled. And so you have number density equals pressure divided by temperature divided by K constant. And that tells you that number density will increase when you increase pressure. And that's not surprising. Okay, increased pressure, molecules becomes more compact. So number density increase. We can expand the collision frequency of this equation further. So in this equation, we have relative speed, we have number density, and the number density we just show equals pressure divided by kT. So plug in here, all right, we have Z equals cross-section area times relative speed times pressure divided by kT. Okay, now the relative speed is square root 2 times average speed. Average speed, we already have that equation, so plug in everything into this equation, and finally we have this equation: 4 times cross-section area times pressure square root 1 over pi m Boltzmann constant temperature. And so that equation, as long as you have temperature, you have pressure, then you can calculate the collision frequency. So at a constant temperature, all right, and the increased pressure increase Z, all right, if temperature is constant. And if pressure is constant, then increased temperature decrease Z constant, all right. And so that's a useful equation to calculate cross-section the collision frequency. Here shows some typical cross-section areas of the molecules. So you have nitrogen 0.43, helium 0.21, carbon dioxide 0.52, benzene 0.88. The larger the molecule, the larger the collision cross-section area, and the more collision it will make every second. Now, we want to calculate the collision frequency for nitrogen at 1 atmosphere, 25 Celsius. So to calculate the collision frequency, we use cross-section area square root 2, average speed, number density. Now we plug in the equation, average speed and the density as we did in the last slides, and here is the equation: 4 times cross-section area, which we choose this number, and the pressure is 1 atmosphere. And now here you have mass of one molecule, Boltzmann constant. So more conveniently, if we can use molar mass, to do that we can times n, Avogadro's number here, and also here Avogadro's number. Now we can times twice, so Na, because Na times m, that's give you the molar mass. So the mass of one molecule times Avogadro's number give you molar mass, and the K constant times Avogadro's number give you R constant. And on the top you have N squared. When you square root, you get Na. Okay, and so here is the equation. So let me erase this. Okay, so that's the equation. Okay, so we have 4 cross-section area pressure that comes from here times Avogadro's number, because remember it's Avogadro's number squared. So now you get Avogadro's number, and square root pi, small m becomes molar mass, big M, K becomes gas constant, and temperature. So plug in all the data. All right, cross-section area. Now cross-section area here is nanometer squared, so you need to change to meter squared. All right, so 1 nanometer equals 10 to the minus 9 meter. So the nanometer squared, you should square it, and that'll give you 10 to the negative 18 meter squared. And then times pressure, 1 atmosphere, which is 1.03 times 10 to the 5th Pascal. And then Avogadro's number, 6.02 times 10 to the 23 per mole. Square root pi molar mass. Remember, molar mass must be in kilogram in SI unit. So 0.028 kilogram per mole. Gas constant and temperature square root. So what we get is 7 times 10 to the 9th power per seconds, and that's the collision frequency. So for nitrogen at 1 atmosphere, 25 Celsius, and the collision frequency is 7 times 10 to the 9th power. In other words, every nanoseconds it will make a collision. Okay, because per seconds it make 10 to the 9th power, and that means every nanoseconds it will make a collision. Another important concept is called mean free path. So mean free path is the average distance a molecule travels between collisions. So let's assume a molecule moves at a speed 10 meter per second. So every second it moves 10 meter, but every second it makes 2 collisions. So 2 collisions per second. That's the collision frequency, C is 2. So what is the average distance a molecule travels between these 2 collisions? It must be 5 meter. All right, so when it travel 5 meter, it make a collision, and then travel another 5 meter, make a collision. So in 1 second, it make 2 collisions and travel 10 meter per second. So in general, the mean free path is the average speed. So in this case, it's 10 meter per second divided by the collision frequency, and that gives you the mean free path. So the collision frequency we just derived is the cross-section area times the relative speed, or the square root of 2 times average speed, and times number density. All right. So use this average speed divided by cross-section area. So you see the average speed cancel each other. So what you have is 1 over square root 2 cross-section area number density, and that's the mean free path. Okay, number density is also calculated by pressure divided by kT. So plug in here, and you get kT divided by square root of 2 cross-section area and pressure. Okay, so so now mean free path is the average distance between collisions. So this is also a measure of intermolecular distance. Okay, so this equation tells you that no matter how fast it travels, because the average speed cancel each other, and so this equation does not have the speed. Speed does not affect mean free path. All right, no matter how fast it travels, the intermolecular distance or the mean free path is determined only by the density. Density is this cross number density, and the size, which is the cross-section area. All right, the larger the cross-section area, the more collisions you make, and the smaller the mean free path. So the mean free path increase if the pressure decrease. So if you decrease the pressure, and the mean free path increase, which is not surprising because low pressure molecules are further away from each other, right? So longer mean free path. And if the collision cross-section area decrease, so if the molecule becomes smaller, all right, the cross-section area becomes smaller, then it will make less collisions, and therefore the mean free path increase. The mean free path is independent of temperature. So if you look at this equation, it seems to suggest increased temperature, increased cross-section area. But when you increase temperature, pressure also increase if volume is constant. So they cancel each other, and therefore the mean free path is independent of temperature with a fixed volume. So here is an example. What is the mean free path of nitrogen at 1 atmosphere 25 Celsius? So we just derived the equation. Mean free path is kT divided by square root 2 cross-section area pressure. So plugging on the data, the cross-section area for nitrogen is 0.43 nanometer squared. All right, so Boltzmann constant, temperature, square root 2, cross-section area must be in meter squared, so 10 to the minus 9 square, that's 10 to the minus 18. And pressure is 1.013 times 10 to the 5th Pascal. So the answer is 70 nanometer, all right? So 70 nanometer, that's the mean free path. Now nanometer, usually a molecule, for example, nitrogen, is about the size of 0.1 nanometer. 0.1 nanometer. So this distance, okay, mean free path is about 1,000 size of the molecule. Okay, it's 1,000 molecular diameter. So combined with the calculations we made before, and it suggests that at a typical gas, for example, nitrogen, at 1 atmosphere 25 degree can be thought of a collection of molecules traveling mean speed 500 meter per second. Okay, very fast speed. Remember, nitrogen we calculation is 475 meter per second. Each molecule make a collision within about 1 nanosecond. All right, and between collision it travels 1,000 molecular diameter. Okay, this also tells you that the distance between the molecules, that's the mean free path, is much larger than the diameter. It's 1,000 times. So, and that means at 1 atmosphere 25 Celsius, the molecules are farther away from each other. The distance and the size of a molecule is so small compared to the distance is negligible. So it's like dots moving in random directions, and therefore it behaves as a ideal gas. So here is a summary of the equations we learned in this section. All right, first we introduced the Maxwell-Boltzmann distribution, which tells you the fraction of molecules at a certain speed. Okay, when you have a collection of molecules, then the molecules will have different speed, some faster, some slow. It's a distribution based Maxwell-Boltzmann distribution. With this distribution, we can calculate the average speed is square root 8 RT over pi m. We can calculate the most probable speed, square root 2 RT over m. And root mean square speed is square root 3 RT over m. We can also calculate the relative speed, is square root 2 times average speed. And using these equations, we derive the ideal gas law, PV equals nRT. And we can calculate average kinetic energy is 3 over 2 kT. And that equation suggests that all gases have the same kinetic energy if temperature is the same. So temperature is a measure of average kinetic energy. The number density is pressure over kT. So the number density is determined by pressure and the temperature. And the collision frequency is the collision one molecule make every second. And it's proportional to the size of the molecule. This is the cross-section area. That's the measure of the size. The relative speed, or the square root 2 times average speed, times number density. So the more dense, the more collisions. The larger the molecule, the more collisions. And the faster it moves, the more collisions it makes. And the mean free path is defined as the average distance between the two collisions. And it is inversely proportional to the size and the density. Okay, it can also calculate by kT divided by square root 2 cross-section area pressure. So these are the important equations we learned in this section.